Welcome everybody, welcome. Thanks for turning out in such great numbers. As Stephen said, this is more people than turned up to his hiring seminar, so he's acted all in. Obviously, he's doing a great job here. So, welcome to the first seminar of the year, the Geography Lecture Series on Climate Change. This is an innovative idea proposed by Joel Wainwright, the chair of the committee, to have a theme for the year's lectures around climate change. I think it's very appropriate. It should be a highly attractive lecture series, and there's 5 outstanding speakers coming up throughout the year presenting cutting-edge research about climate change from different fields, including geography. And our first speaker this week is our own Stephen Quiring, who is, I think, now in need of very little introduction, but I will give you some. He's a climatologist with research interests in hydroclimatology, synoptic, and a huge number of research projects under many different categories. You've seen his cluster of students, his funded research, frequently mentioned in our Friday updates and news. So Stephen's a very active research worker with a great team. And since completing the PhD in climatology at the University of Delaware in 2005, he's published a large amount of research in climatology, but especially in land-atmosphere interaction and modeling the impact of weather systems events, such as hurricanes, on power systems, which is extremely timely. And as you may know, Stephen and his colleagues produce a forecast of the impacts of hurricanes. So today it will be our distinct pleasure to hear, I believe, your first research talk back here since you were hired. So welcome back. And let's join me in welcoming Stephen to the department. There's another chair here, by the way.
Yeah, there are a few, 2 maybe, chairs available. So good afternoon. I know there are some people who have to sneak out. It is Friday afternoon. You're not going to offend me. Just good luck taking through the chairs when you have to do that. Joel promised me I had like 3 hours, so I've tried to compress down what I wanted to say to fit that 3 hours. No, okay, it wasn't 3 hours. Okay, so this is an area that I've been working on for. This is kind of my intellectual passion. So we have projects that pay the bills, and then we have kind of our intellectual passion. And so for me, understanding what causes droughts and looking at land-atmosphere interactions goes back to my undergraduate days at the University of Winnipeg, where, like some of the geography majors here, it was a discovery major for me. I started off in computer science, took a geography class, and realized that, oh, this is pretty cool. They talk about climate and they use computers to do this stuff. And so my family, the family kind of background from the Canadian prairies is in farming. And so drought has a huge impact in terms of farming. And so this is, I think, kind of why I grew up with this idea. My grandfather, my mother, all of my aunts and uncles who were involved in farming kind of watched the weather very carefully. And we're always noting and trying to predict and relate weather conditions to what would happen with the crops on the farm. And so that's kind of how I started this some number of years ago, which we will mention. All right. Oh yes. So this is a slide that Joel asked me to put in, if it works. Okay. Yes. So this is his slide. I don't do animations in PowerPoint, but. Like was mentioned, there are other great talks this year. We have things organized. We hope that all of you will be back for the other events that are coming up, including the next one on October 5th. We'll encourage Joel to find a larger room so that we can invite all of our friends to come out as well. All right, so one of the pillars in my research program is related to soil moisture. And soil moisture is important both from an energy standpoint and from a water standpoint. So as a hydroclimatologist, I'm very interested in looking at the land-water balance and understanding the supply of water, the atmospheric demand for water, the cycling of water through Earth systems, And soil moisture plays an integral role in that. So here, soil moisture we can see as influencing what happens in terms of recharge and runoff, and also directly influencing what we see in terms of evaporation from the land surface and transpiration to the crops. On the energy side, we could see that soil moisture plays a critical role in influencing the partitioning of latent and sensible heat. And so, given a set amount of incoming solar radiation, soil moisture is the variable that determines how much of that energy ends up being used for evaporation of water, transpiration of water, and how much of that energy is used to heat the land surface and ends up as sensible heat. And so for these reasons, as a geographer, as a physical geographer and a climatologist, I view soil moisture as one of those critical integrative variables in the Earth atmosphere system, that to really understand soil moisture, you have to understand land use, land cover, you have to understand the topographic position, the geomorphology, the history of that soil, how it formed, what it's made up of, how it's structured. And so really when, this is why I gravitate towards soil moisture, and it's also an area that has traditionally been under-measured, at least in terms of in situ measurements. And so this is how I carved out a niche for the NSF Career Project that helped to build the North American Soil Moisture Database to pull together these observations so we can do the kinds of studies that we're interested in, looking at land-atmosphere interactions, which before we had to go to individual networks and there was not a homogenized, standardized data set. So if we look at what the relationship is here between soil moisture and evaporative fraction, so on the vertical axis here we have evaporative fraction. We define evaporative fraction as what fraction of the net radiation ends up as latent heat. And we can say that there's an upper limit to this, and this upper limit is determined in combination by what the available water is from soil moisture and how much energy there is. And so we can look at different kinds of regimes that exist in the world. We can say in dry locations, like deserts, there might be lots of energy, but there's no water, so our evaporative flux is going to be really low. We can say in tropical environments, there's lots of water, but there is some upper limit to energy, and so those are places where the water typically, or the energy typically limits. You can also think of this over the world's oceans, that these would be places where it's the net radiation that limits how much evaporative, what the evaporative fraction is, how much latent heat there is. When we look at transition zones, and not just in hydroclimatology or this topic, but transition zones are often very interesting geographically and climatologically. So in this case, a transition zone where we have sometimes soil moisture being a limiting factor, sometimes energy being a limiting factor, and precipitation is neither extremely high or extremely low. These transitional environments are particularly important for land-atmosphere coupling. And so you can take my word for it, or Sonia Senabrotny's, or you can look at a classic paper that was published in Science in 2004 by Randy Koster. And so this uses, this was a modeling to comparison project where they were looking at land-atmosphere coupling strength, and the color here is the coupling strength. The warmer colors indicate higher coupling strength. And these regions with the boxes are three of the locations, three of the global hotspots for land-atmosphere interaction, where soil moisture plays this critical role in governing what we see in terms of fluxes from the surface to the atmosphere. One of these transitional zones, as shown in this diagram right here. And so this is kind of what, you'll note that the region that we're going to talk about today is not the only region in the world where this is important, but it's the one that I've focused on for most of my work, partly because of data availability, geographic convenience to where I've been located. And so we'll focus mainly on the central US, and this is important because this is one of the places where land-atmosphere interactions are hypothesized to be and shown to be in models to be really important. So I mentioned that the motivation behind this was understanding drought. And obviously most droughts are not caused by land-atmosphere interactions. Most droughts are caused by internal variability in the ocean atmosphere system, particularly SST-type forcings. And so the Pacific Decadal Oscillation, the Atlantic Multi-Decadal Oscillation have all been shown, demonstrated to cause significant global droughts. And in fact, there's a really good paper in Science called The Perfect Ocean for Drought, which shows what some of those global SST patterns are that are linked to past droughts like the 1930s and 1950s. So I don't want to say that, even though I'm saying soil moisture is important, I don't want to say it's the thing. It's a thing that can contribute and exacerbate a drought, especially once it starts. And so here we're talking about feedbacks. And really what we're trying to understand is, does soil moisture have a positive feedback, which says when the soil is wet, that increases evaporation, it increases transpiration, it increases the humidity in the lower atmosphere, it lowers the level of lifted condensation, lowers the atmospheric temperature. So is it primarily a wet or positive feedback that drives this, which would say that wet begets wet? Or is it a dry soil feedback where as the soil gets drier, we see that evaporation decreases, transpiration decreases, the surface temperature increases, the temperature of the lower atmosphere increases, it pushes up the planetary boundary layer, the layer of liquid condensation level, and creates lift at the surface. And so this is actually an open question, one of those unsolved debates in the literature. If we look at what global climate models show, global climate models primarily show that it's the wet, positive feedback that dominates. And that was sort of uncontested until this 2012 paper, which is based on observations by Chris Taylor that was published in Nature. And this paper shows everywhere that is a red square, shows that there is a statistically significant preference for afternoon thunderstorms to occur over drier than normal soils. So this would be our negative dry soil feedback mechanism dominating. He used the exact same methods and then applied it to a variety of climate models and to also some reanalysis products like Mira and Mira Intern. And the big takeaway between these two slides is that here we have mostly red. Here we have mostly blue. So the models are showing predominantly a positive wet soil feedback. The observations are showing a dry negative feedback. And so that is kind of the motivation for this work. So we'll see what. So why does this matter? Why worry about land-atmosphere interactions and feedbacks? What's the big deal? Well, if we look at future climates and we try and understand what water resources are going to be available, our understanding of future hydroclimate comes from these same models that were shown to have a different signal than was seen in the observations. And in fact, if we pull out the AR5 report and look at the high emission scenario, we can say, okay, there's some significant locations of increased precipitation, northern hemisphere, high latitudes, over Antarctica, in the tropics. There's an expansion of the subtropical Hadley cells and drying. And importantly, there's a lot of places where there's not these little dots, this little stippling pattern, or the cross-hatching pattern, which are places that then indicate there's uncertainty in the models. And in particular, if we look at some of those places that were identified as hotspots of land-atmosphere interactions, those are coincident with these places of lower agreement between the models. So one possible way to help resolve some of that agreement is to get a better process level understanding of land-atmosphere interactions and solve kind of this equation. So this is one of my favorite slides. This is not actually AR5, but this is from AR4. And these are 21 general circulation models showing projected precipitation patterns over North America. So here's the outline of North America, blue, getting wetter, red, getting drier. And these models are just stacked up, 1, 2, 3, 4, 5, 6, 7 in a row, 3 rows, 21 models. And this is not one of those, stare at the screen and the 3D unicorn kind of pops out pictures, although it kind of looks like that. It's to pick your favorite place in North America. I won't ask you to point out where that is, but pick your favorite place and look at it across these 21 models. So these are the state-of-the-art climate models. Now, not quite the state-of-the-art because it was AR4, but qualitatively, I could reproduce this same pattern using the 32 models that informed that previous RCP 8.5. And you will see that even on this multi-decadal average of annual precipitation, that there are significant differences and disparities from one model to the next. Therefore, when we average them all together, like we did here, we get these regions where we don't really know exactly what is projected to happen in the future. And there's lots of reasons for that. And there's lots of smart people, including some in this room, that are tackling various aspects of this project, understanding those ocean atmosphere feedbacks and the role that they play in future precipitation patterns, sub-grid scale processes, clouds, aerosols, a whole host of things. So land-atmosphere interaction is just one component, one piece of the puzzle. But it's the piece that we're going to look at today, and the reason is that we want to improve our process level understanding of these feedbacks so that we can improve the accuracy of our projections of future climate. How are we going to do that? Well, we're going to travel to the state of Oklahoma. And the state of Oklahoma turns out to be the center of the universe when it comes to soil moisture research. And it's the center of the soil moisture universe when it comes to research because of one simple thing: observations. And so there's people in this room who feel passionately about observations like I do. Observations are the best way to confront remotely sensed data or models, to determine, to understand what's going on in the climate system. And observations often constrain what we can do. So when we look at that multi-model uncertainty, we can see places where we might like to have more observations, so we can determine what's going on and which models are getting it right and which models are getting the processes right. So this is work that was part of that the NSF award that I had at Texas A&M. I'm the lead author on this, former PhD student of mine, Trent Ford, who's now a professor at Southern Illinois. And so his doctoral work was looking at land-atmosphere interactions in Oklahoma using observations and trying to answer this question: does afternoon convection occur preferentially over wet soils or over dry soils? And what are the processes, what are the physical mechanisms that are linked to those events? So to do this work, we gridded the data from the Oklahoma mesonet. So we have in-situ observations at a 25-kilometer resolution. We looked at just the 5-centimeter observations, just the data from the morning, before the afternoon. We used data from 1998 to 2014, and then we identified what here we call unorganized convective systems. You can think of it as popcorn convection or weakly forced convection. We don't want to look at things like a dry line or a cold front or Hurricane Irma moving over the eastern United States. The reason is that those are not events where we would expect that the land surface plays a leading or strong role in causing precipitation to occur, or in most cases influencing precipitation. We sometimes see exceptions: Tropical Storm Erin, sort of reforming over Oklahoma, the brown ocean effect, as Marshall Shepard likes to call it. So there are some examples of even where with large synoptic systems we see interaction with the land surface, but those are not our ideal scenarios to extract that kind of signal. Then we use some radiosonde data to look at soundings, pre and post convection. And we're focused here on the warm season. Again, this is when we expect, afternoon in the warm season, when we expect this kind of convection where the land surface plays an important role. So this is a schematic of the manual classification system that Trent and an undergraduate student at Texas A&M, Jenny Blake, undertook for those 11 years of data, looking at radar data every 15 minutes and identifying the location and timing of these unorganized convective systems and filtering out all of those large-scale systems. This is pretty labor-intensive, and the manual method is not very good, so this kind of leads to the next project, which you'll see the stuff that we're doing now, the smarter way of doing it. This is the harder way. Eventually we get to the smarter way. That process resulted in 477 events that occurred after noon local standard time and just days where there was not rain in the morning. So we want days where the morning soil moisture is unaffected by precipitation earlier in the day, and that those storms formed or popped up for the first time sometime in the afternoon when that accumulated effect of the land surface, either the evaporation from the land surface or the heating, sensible heat fluxes from the land surface could have affected it. And we're looking at the point of initiation. This is kind of minor, but Chris Taylor's work, they looked at the point of maximum precipitation, which is perhaps one of the, anyways, that's an aside. Well, that's more of a Thirsty Thursday conversation for a large seminar. But there's lots of methodological questions that one can get into. This is where those 477 events occurred. We did look to see if there were things like gradients in land use or circulation or other things that caused it. We didn't see any sign of clustering after passing it through some spatial statistics tests. And then we extracted for each one of these events the soil moisture underlying that event when it occurred and clustered these into bins. And so this is soil moisture percentile. So 100% is the wettest that location has ever been climatologically. The lowest bin here is the driest. And so we just, for each location, standardize it based on the historical distribution at that point, turn it into a percentile. This is median or normal soil moisture. And so you can see that, okay, there's a few more events over here, and you can do a difference of means test and see that there's a statistically significant difference. We resampled using a bootstrap methodology to do this thousands of times and see what's the chance of deriving this distribution by chance. So we can say that there is a preference, but there's certainly a lot of events over here on the wet side, but like Chris Taylor, we find a dry preference overall. We can break that apart a little bit more. So we can say everything below the 50th percentile is a dry event, everything above the 50th percentile is a wet event. We can look at count the number of wet and dry events in a given year. And perhaps, not surprisingly, when you have a wet year like 2007, there's a lot more wet soil events, because there's frankly not that much dry soil in Oklahoma that whole year. And with drier years like 2006, 2011, 2012, it's the dry soil events that dominate. So there are certainly variations over time in which mechanism is leading, wet versus dry. There's variations over space. We're just looking at Oklahoma here, so we're not going to show sort of continental patterns, but we can use this kind of methodology to do that. And we can see overall that there's a slight, there's a seasonal, within the growing season kind of preference. So this is the mean monthly precipitation in Oklahoma. And you can see that the number of events increase both in the wet and dry soil categories. There's more events in June and July than there are in September and May. And I'll skip this one, but that's just another way to slice and dice the data. So that's answering the question, wet soil or dry soil. There is a dry soil preference that tends to support what Chris Taylor found in a global analysis. It tends to contradict what all the models show. Now, why? What's going on within these individual events? So here's where we use the soundings. So we look at Lamont, Oklahoma, a place where we have soundings twice a day that we can look at what's going on then. We have data from the mesonet at the surface. We have atmospheric data from the soundings. Now, we only extracted events that occurred within a representative distance. I think it was 50 kilometers of Lamont. So that goes from 477 events down to 19. So sample size issues start to show up. We then clustered these data using convective triggering potential and humidity index, just a way to examine classify them in terms of land-atmosphere interactions. The clusters are shown here, so there's basically these number of events in each one of these clusters, and you can then look at the relationship. So these are greater than the 50th percentile here. These are our wet soil events. These are our dry soil events. And so if you look at the wettest events and you look at how did the surface temperature change from the morning to the afternoon, not surprisingly, less change in surface temperature when the soils are saturated because that energy is going into latent heating instead of sensible heating. Conversely, with the dry soils, we see large changes in the surface temperature between those two times. We can also look at the planetary boundary layer height and see that there is a similar pattern that for the wet soil events, we see a much smaller change in the planetary boundary layer height, much less growth in the planetary boundary layer over the course of the day versus the dry soil events. We can look at other things like changes in convective available potential energy between the morning, the 6 a.m. and noon local standard time, and we can look at changes in convective inhibition and note that these are negative changes here, so and that the zero line is right here. So for example, over our dry soil conditions, not much change in Cape over the course of the day. Not surprising, we're not having much local addition of latent heat to the atmosphere. Over some of the dry, wet soils, we see larger changes in Cape and more constant convective inhibition, less change in convective inhibition over the wet soils, more decreases in convective inhibition over the dry soils. Update our software, right? We can also summarize all of these data. So there was those 4 bins that we had before, wet to dry, and we can look at the Cape at 12Z, the Cape at 18Z, the lifted condensation level, et cetera, et cetera. So over the wet soils, we had much more precipitation, larger precipitation events, number of radar pixels that were in there, longer precipitation events, larger and more rainfall. And we can see that the contribution, the mechanism that's going on here is different between the wet and the dry. So what this study sort of told us is that, yes, soil moisture does have an influence on the near surface atmosphere. We can measure that with the sounding data and with our Mesonet data. We see examples of both unorganized convection events occurring over dry soils and wet soils. So perhaps the question isn't so much about which is most important, but when is each important and where is each important. And we can see that there's evidence for the different type of mechanisms working for each of these kinds of events. And so we can see changes in the lifted condensation level, level of free convection and Cape, higher Cape over wet soils, higher sensible heat, a higher planetary boundary layer, and decreased convective inhibition over the dry soils. So there's significant variability here in the sign and strength, meaning wet soil or dry soil, and how important this is over this study period. But there's a lot of limitations to what we just did. I mentioned the manual method. Surprisingly, I had another graduate student volunteer to do that manual classification over the world for 20 years. We only looked at Oklahoma, which, it's great. If there's people from Oklahoma, yay, Oklahoma, but it's just one state, and how representative is it globally of these processes? We have sample size issues, especially when we go down to the number of events that are co-located with soundings, and with in situ data, it is a point. So a soil moisture sensor is literally measuring a volume, depending on the sensor. It's a cylinder, it's about this big around, and if you think about how variable soils are, we could go outside this building. I wouldn't recommend this because there's probably some OSU police that'll come jump on us if we dig holes in the lawn out there, but we could measure large differences in soil moisture in very small distances. And so how representative are those mesonet sites of what's going on in that 25 by 25 kilometer pixel centered over that location? Finally, we know that although the land surface conditions are important, it's also the gradients in soil moisture that. And so that leads us to what work we're doing now. So about a year ago, we received funding from the Science Utilization of SMAP NASA project. The SMAP mission was, the SMAP satellite was launched in January of 2015. And the SMAP satellite is the latest and greatest NASA satellite for measuring soil moisture on a global basis. Maybe somewhat less great since it was supposed to be, as the acronym suggests, soil moisture active passive. Now it used to be SMAP, now it's SMOP, I guess, because the A died. So the active, the radar failed about 6 months after launch, which is kind of an expensive $800 million mistake. These things do happen, and so as a result, we now have the soil moisture passive mission. NASA's recently released a new product using Sentinel, which uses the active from Sentinel with the passive from the SMAP satellite to replace some of the products that were going to be part of this mission. So the advantages of using remote sensing over in situ data to do this kind of study is that we have near real time, nearly global coverage. We have a good understanding of the calibration, the errors. We have a spatially complete product, and we can look at things at relatively high resolutions continuously. There are some issues with the SMAP satellite. It has difficulty retrieving soil moisture when there's dense vegetation, so not very good for forested areas or high biomass areas. There are errors and uncertainties associated with the retrievals that contribute to this, and NASA says 2 to 5 centimeters is probably like 2 to 3 centimeters is the depth of soil moisture that you're retrieving with the SMAP satellite. So this project is in cooperation with Trent Ford, who's now an assistant professor at Southern Illinois, and Adam Houston, who's at the University of Nebraska. And the part I'm going to talk about today is evaluating whether deep convection occurs preferentially over wet or dry soils, but now using satellite data, which allows us to go from 400 events to 16,000 events. So the reason we teamed up with Adam is because he is the creator of this Thor product, which if you're going to come up with acronyms, Thor is a pretty good one. Thunderstorm Observation by Radar algorithm. And so the advantage of the Thor algorithm is that it is an automated way to do the Trent Ford and Jenny Blake detection of events. So it uses radar data, it uses lightning data, it uses NAR storm motion to identify the location of convective initiation, and then to track that storm throughout its life cycle. And so we have lots of convective initiation points, we have velocities, and we have lots of detail about this. We can do this for a large area for a long period of time. Yes, it grinds through some supercomputer cycles, but when it comes out the other end, we have a very rich data set to use for this. This is something that he's developed for the last number of years. The individual details of this are all in his 2015 paper. I won't go into the weeds on his methodology, but just to say it uses lightning data, level 2 radar data, NAR storm motion grids, and then his multi-stage algorithm to identify the point of convective initiation and then to track the storm throughout its life cycle. So for this particular analysis that I'm presenting today, I'll show the data from 2005, 2006, 2007. These blocks here represent the area in the central United States for which we have points. This is a nicer way of looking at it because it takes all of these dots and averages them for a given year. So this is the location of convective initiation in 2005, smoothed with this kernel density to show you the number of values per square kilometer. This is just plotting them all in MATLAB, and they're all on top of each other so you can't see too well. But there are 16,083 or 4 of them. They're all from the afternoon And we filter out all the ones where precipitation occurred within the morning. So it's just days that it's afternoon rainfall. And just note these 5 by 5 kilometer boxes, which are in yellow and almost invisible. But there are 12 of them, and some of the results in future slides are reported for these boxes. So the SMAP satellite was not up in 2005. The Thor data algorithm we're now running back from present, and so once we have data for 2016 and 2015, we'll be able to add those into this analysis and use SMAP as our soil moisture. However, there were some previous satellites that we can use to look at soil moisture in 2005, 2006, and 2007. Rather than pick one, we're using all of them. And we'll show you why it matters in a moment. So AMSRE, TRIM TMI, and the European Space Agency's Essential Climate Variable Soil Moisture, which is a blended product that tries to produce a really long time series that blends multiple satellites together. We're again focusing on the warm season, and to standardize all of these products, we've turned them into anomalies by subtracting the mean and dividing by the standard deviation, using a 15-day window centered on the day of the initiation, and using the entire climatological data set, the entire historical data set, to determine what the mean and standard deviation at that point, at that time of the year are. Important to note that TRIM has some limitations. So the northern part of our study region, we don't pick up in this case. So the number of events that we have when we do the TRIM analysis versus the AMSRE analysis or the ECB analysis is a little different. These have all been regridded to the same resolution and matched to the timing of that product. So, lest you think this is too easy, we do have some manual methods involved here. And this is to go back to determining which of these, so we have 16,000 events from Thor, but which of those are associated with cold fronts? Which of those are associated with dry lines? Which of those are associated with an upper level disturbance or trough? In other words, which are the ones that are the baby that we want to throw out or keep, and which are the bathwater that we're trying to separate. And so the way that we've done this is, again, to look at all of the days in 2005, 2006, 2007 over this region and subtract out, remove any points where there is a synoptically forced event, a cold front or a dry line or one of these other features that we are less interested in for this analysis. And this shows the number of events that are to the left, the number of days with weak forcing. And this shows the variation by region. So you can see in some regions, only about 10% of the warm season days are candidate days. In other regions, West Texas, Red River Basin, Louisiana, we see that there's a larger percentage where we have that pop-up convection where the land surface may be playing an important role. So the way that we determine statistical significance is by resampling. And so bootstrap resampling with replacement is our preferred approach here. So we have 16,083 events. We know convective initiation. We know soil moisture at those locations. We grabbed 16,083 points randomly 1,000 times. And then each of those distributions shows us what could, if there was no relationship between soil moisture and convective initiation, that provides our background signal to say, for these weakly forced events, do they separate out from that, that random sampling? So that's what I'm going to show on the next slides, and we can also then calculate a significance for these. So before you say something with WF in it, I'll explain what these are. So soil moisture anomalies along the bottom. Each one of these blue dots is the mean from our 1,000, of one of our 1,000 random resamplings of 16,083 points. And the black lines are the distribution that show the soil moisture anomalies for all of those events. And all these black curves are over top of each other, so you can't see that there's 1,000 lines right there. The red represents our weekly forced events. And so the red, what we're trying to look at here, plotted looking at soil moisture, so negative anomalies here suggest drier than normal conditions. And the soil moisture anomaly here is the variability between events. And so if we use all 16,083 events from that 3-year time period and compare what are the soil moisture conditions like under those weekly forced events to what they would be under a random selection of events, we can see that there's a systematic separation, a statistically significant, it turns out, separation between this cluster of random points and our observations that show our observations based on one satellite product, answer E, are statistically significantly drier. So this supports Chris Taylor's finding and says that there is a dry preference, that a tendency for these storms to occur on drier than normal soils. And if we look at the same analysis, now just looking at the weekly forced events, those ones that we subsetted to, we can see that the same signal is there and that the difference now is larger. And these results are hot off the press, so if you notice, I have not standardized my axes, or in this case Trent has not standardized his axes, so that we can't compare the distances here. We have another slide in a moment that shows that, but you can see that this minus 0.25 is greater than this minus 0.15. So that's finding number one. So we repeat the same analysis. Now we use a different satellite product. Oh, surprise! This red dot is statistically significantly greater than 0. So there's a preference for these events to occur over wetter than normal soils if we do the exact same analysis and just switch the satellite product. If we now look at trim TMI, so these two products, I should note, AMSRE is not, oddly, statistically independent of the ECB product because AMSRE is one of the products ECB uses in its satellite blending. Trim TMI is a separate, independent from both of those, and it also shows a preference for wetter than normal conditions. And so we'll stop there and summarize for a second. So the convective initiation points are the same. The methodology is the same. The resampling is the same. The only thing that we've changed in this analysis is just the satellite data product to tell us how wet or dry the soil is. And if we summarize that on this slide, so this is our soil moisture anomaly, 0 is right here. And so if we look at AMSRE with all our 16,000 points, we get a slight dry preference. If we look at the weekly forced events, that becomes a larger and more a larger dry bias. You can see that the width here of the whiskers is because there's more events in the all than there is in the weeks, or uncertainty is greater in these 3 week categories. If we switch to ECB and look at all events, there's a wet preference. If we look at weekly forced events, that becomes a stronger wet preference. And if we look at trim TMI, all events, there's a weak preference. If we look at weak events, there's a stronger wet preference. Now, the other reason we plotted these whiskers on here is so that you can see, are these statistically significantly different from one another? If the lines with the triangles, these lines overlap, then we can't say that they're statistically distinguishable. So in the case of AMSRE, the weak events do show a much stronger signal than all events. For these others, there's not a separation between them. So that's one axis that we can use to look at the results. It's not the only way, though, that we've sliced and diced the data to see how robust this signal is. The other way of doing this is to look at different ways of classifying weakly and strongly forced events. So we might say, oh, back here, it looks like the difference between the weekly and strong, or the weekly forced events and all events is fairly large. I wonder how sensitive it is. This was done manually, and surely, humans are imperfect, and what if they just pulled the wrong events out, and that's really what's going on here. So it turns out in the literature that there are a variety of methods that one can use using the upper level winds, the storm velocity, and other variables to classify whether events are weakly or strongly forced. And so we redid the analysis with two of these other methods, one from Tom Moat's group at the University of Georgia, one by Andrew Carlton at Penn State. And so we take those 16,000 events, apply them through that method, and see how much overlap there is. I didn't show that to you here because I didn't want it to get to 6 o'clock. So, but we then did an ANOVA, two-way ANOVA, fun, good way to look at the data. And what this tells us is, which of these things matter? So we already know that the data set matters, right? If we group things by the data set and by the convective forcing, and do our two-way ANOVA with interaction, we can see the data set matters. The forcing, it turns out, doesn't matter overall, but the interaction between those does. And the reason why the interaction matters is because for AMP-SIRE and the forcing, there's a difference, but for these others, there's not a difference when we look at weakly and strongly forced. Then we can do the same thing at ANOVA with looking at the data set and the classification method. We can say again that yes, the data set really does matter. The classification does matter. There is some differences between the classification, which I haven't shown, and the interaction between those matters. So why do this? The reason that we did this is because there are some very strong stances taken in the literature about methods. Like, this is the right data set to use, or this is the right way to separate out weakly and strongly forced. And so it turns out that if you take one of those really strong stances and you only use that particular mechanism, and there's a couple of leaders in this field who are often get asked to review papers on these kinds of topics, and they have their particular issues that they like to make sure are characterized in your paper. And so as a result, that pushes things in a particular direction, that pre-selects for what the answer is going to be. And so what we're hoping with this paper, with this analysis that eventually we'll wrap up and submit, is to show that methods and data sets and these arbitrary or subjective or maybe even objective decisions that you make influence the results and feed back to our answer about, is there a preference for wet soils or for dry soils? So for the graduate students, we sometimes harp on, I'm not sure what the right word is, harass, encourage, instill some ideas about methods and doing a robust analysis and the sensitivity of the decisions that you make along the way in terms of data sets and methods and all these things, and this is why it matters. That the answer that you get in this case changes just by changing the satellite product. The answer changes depending on how you classify weakly and strongly forced. All right, so I'll get off my soapbox. So what have we found from doing this analysis? There's a different answer depending on which data set you use. And there's substantial variability in the sign and the strength of this soil moisture precipitation coupling. If you want me to give you a wet positive forcing, I can pick data sets and methods to give you that answer. If you want a dry negative feedback, I can pick data sets and methods to give you that answer. So which one is right? That's the harder question. We don't really know, and that's where the future research comes in. And so to tie this back into climate change and to why I'm passionate about this topic and why I think land-atmosphere interactions matters, not just for the Great Plains or for Oklahoma or for people who care about in-situ soil moisture, an open question in my mind is, do the models accurately capture land-atmosphere interactions? I would like to say, as an observationalist, that we can use observations to confront the models and determine what the right answer is and compare the models to those observations and see if can they reproduce it. But I just showed you, well, which observations are we going to use? So we want to make sure that the next generation of global climate models, earth forecast models, accurately capture land-atmosphere interactions, because land-atmosphere interactions have a huge role to play in drought, especially extreme drought. So the 2011 drought in Texas, drought of record for many places in the southern United States. Billions of dollars of damage, agricultural losses, crazy forest fires in Texas, the Bastrop area, devastated by wildfires. Millions of trees in the state of Texas died, lots of bad things. That drought is one where land-atmosphere interactions, the drought wasn't caused by land-atmosphere interactions, but the severity of the drought was exacerbated by land-atmosphere interactions. And so if those kind of conditions set up more in the future, are we going to move to, so this is one particular, I put this up just not because I actually endorse this paper in any way, shape, or form, but because it shows trends in future drought. And it's a nice way of encapsulating this. There's some issues with this paper. You can read all the responses and rebuttals to it. But this is showing the Palmer Drought Severity Index and trends in the PDSI from sort of a more recent decade to one that's further in the future. And as things get into these red and purple colors, that's bad. That's a trend toward increased drought severity, worse conditions in the future. So we want to be able to use global climate models to actually produce reliable pictures of future drought conditions. We may not be at a place where we can do that. And so my interests in the ongoing work with the NASA project will be to investigate how do these land-atmosphere interactions vary over time and space. We'll be able to have a very long record. So in 3 years, we had 16,000 events. We're going to come up with an 11-year record, which should give us 5 times that amount. And that will certainly allow us to characterize, at least for this part of the world, how those patterns change over space and time, look at individual drought events, look at the physical mechanisms that are involved, and then hopefully contribute a process level understanding that can help improve this last point of looking at how will the frequency and severity of future droughts change and what role the land-atmosphere interactions play in that. And with that, I will conclude. I will just mention there's 3 people in the room who have contributed to this project. Shan Shui, Yu Chun, and Lisa Goldstein, who's an undergraduate student here at OSU. And then there's a lot of people at other institutions who have been involved. So I'm just the one who gets to stand up and kind of talk about the research, which is really exciting. Of course, they're the ones who have actually done most of the work. So I'm happy to take questions. Also, if you're one of those 10 people who told me they have to leave early, sneak up now. Yeah?
What is sounding? What does it mean? You said you have soundings of... Could you explain that for the non?
Sure. So kind of like the blimp lab, right? So we send up a package of instruments and measure atmospheric temperature and humidity in the profile of the atmosphere. And so these radioson sites are unfortunately relatively scarce. And so we can only, in this case, we only do this analysis for Oklahoma close to where we had a radiosonde, a regular balloon launch.
So what is relatively scarce? Like how many in North America?
Oh goodness, someone who actually looks at the
About 300, is it something like 300 in the United States?
Upper air.
Upper
It's
air.
like 40.
50, yeah.
Yeah, I was gonna guess like.
And this is a data-rich environment?
So this is an important point, right? Observations are pretty important. And it's great to like produce models, and I love supercomputers, and you can do like million-year simulations, and it's awesome. But eventually you might want to determine like how realistic is that? And unfortunately observations are not that sexy, they're expensive, they're difficult to maintain, people don't want to necessarily put money into that. So in Texas I spent a decade trying to get a Texas mesonet because observations, all the research done to the north in Oklahoma, which if you're from Texas is like bad. But we didn't have the data to do it. And so similarly, you know, Jim and others are interested in enhancing observations in Ohio in terms of a mesonet and measurements. And for soil moisture, it's the same thing. There's a dearth of soil moisture measurements. So satellites are great, but we could also have the satellite like validation versus in situ talk if we want to see some like really shotgun scatter plots. So yeah, eventually we need observations.
Kind of going off of that, I'm just curious, do any of those satellite projects correlate the best with actual soil moisture measurements?
Right, so that's a great point. In this analysis, we just treated them as equal, different but equal, separate but equal, whatever. We may want to weight those or pre-select for the most accurate. Since our sponsor is NASA and the SMAP mission, our thinking is that, hey, we'll use the SMAP mission because it's the latest and greatest. Once we get our Thor analysis done for 2015, 2016, 2017, we'll use SMAP as an additional point of comparison against these others. There are a lot of validation studies that have been done. The challenge is, a very common geographic challenge, scaling. So the soil moisture measurement is a point, and the satellites are integrating over a pixel, and we don't have very many locations where we have enough in situ measurements to accurately upscale it to the resolution of the satellite. There's a lot of methods to also downscale to a finer resolution from the satellite, and those also have uncertainties. So this is, yes, what is truth in this case is a legitimate and difficult question to answer. Jim?
The Oklahoma mesonet, they have soil moisture at multiple depths, right? They have at least 2, right? They have 5? Okay, so the next one down, you use 5 centimeters, and the next one down is 10, is that right? Or I don't know, one of the depths. I'll just stop that question. I'll go to the next question, which is, so did you look at different depths to use for the analysis, and is this one the one that works best, or how did that work out?
Yeah, so another question we were asked by reviewers, why 5 centimeters? That's not integrating over the root zone. And you know, if we're looking at transpiration, whatever, we should be looking at, it turns out it doesn't matter. The 5 centimeter is chosen in this particular analysis because it's the closest to what the satellites give you. And so this puts us on kind of a more comparable footing. But if we integrate over the root zone or take a deeper depth, qualitatively there's not a difference in the answer. Yeah, it is kind of interesting that the 5, so there's some implications for that. If you think about how do you want to save money on deploying measurements, if you can, with the 5 centimeter, get enough information that you can also, and Ning's work shows this, you can also estimate pretty accurately deeper in the profile, then you don't need 5 sensors. And putting in the one at 100 centimeters is that's the backbreaker.
This might be tangentially just relevant in that manual classification is supposed to Thor. How good is Thor? How does it validate? Is it validated? I mean, it's probably in the 2015 paper, I know.
Yeah, good question.
But
yeah, so correct. I have not asked that question. We are consuming Thor as if it is truth for the identification. We could compare Trent's manual identification to Thor there and see how well they interact. In this case, because Adam's a new collaborator, I haven't put his method through the meat grinder yet, but I should. Yeah, that's a good question.
Steve, so when you, at the beginning, you were saying positive feedback, negative feedback. So do you mean in the wet clear case, that's positive feedback, the other is negative feedback. So from that perspective, it's not clear it's positive and negative feedback. You are looking at the synoptic events, right? It's a great going to the mechanism. Have you looked at sort of from a longer time scale perspective? For example, if you use monthly data, one, can you identify feedback? I did that for the vegetation, so that's why
Yes.
So I'm
Yeah,
wondering,
so
have you-
very common in the modeling literature is looking at feedbacks on kind of monthly or
Yeah.
seasonal timescales. And we've done that with the in situ data and with the model data to kind of look at
Right.
those relationships. In this case, because we want to get at mechanisms,
Yeah.
we're trying to drill down to the event, like a
I
specific.
understand.
But
My point is that in your observation, if you use those kind of methods, what's your feedback? Is it positive, negative? That's my question.
Sure.
Or it's unclear.
For the monthly timescales, the positive feedbacks the wet soil leading to more precipitation dominates.
Even regardless of the data set.
We haven't redone it with the satellite data sets here, but with the in situ and the model, that's the
I
case.
see. Okay. Yeah, okay. Well, so does that mean the synoptic view is not explaining the monthly, or is there something else going on in the monthly case? Beyond what you're looking
So I think it's about the relative frequency of the weekly forced events versus, like, so how important are the weekly forced events versus the synoptic cold front,
Right,
dry
right,
line,
right,
whatever.
right.
And it turns out that those synoptic type events they're more frequent, they contribute more precipitation, they're maybe 80% of the picture. And so we're really looking at, we're drilling into that 20% to understand that.
But as far as the feedback is concerned, maybe the longer term one is still better, is that right? I mean, if you use monthly data, you supposedly did feedback analysis. And like you said, if it's small, dominant by feedback. Is that reasonable? I mean, do you think that's...
So could we get a different feedback at different scales? Is that the question? Or
No, I'm wondering, if you did this with, suppose you have satellite data, a different satellite data, you did the same thing, is it possible you get a consistent feedback in monthly data and not for this event?
Oh, yeah.
That's my
That's a good question. I don't know the answer to that.
Yeah,
But
okay, so
that's a good question
Yeah,
that we
yeah,
can
yeah.
look at. Yeah. Someone has to tell me when I'm supposed to know this up, but yeah.
Well, so maybe you could just step back and tell us, like, as a scientist, what is it like to be committed to a form of data which is actually not giving you the answers you want? I mean, you haven't quite hand modeling, but you suggest that, modeling needs to be ground truth or something. And yet, the sorts of stuff that you've done does not produce any sort of conclusive evidence. It produces a nice puzzle for sure, but it doesn't give us a sort of conclusive evidence that we usually associate with advocacy for one model over, or for, in this case, for in situ measurements of the models. So how do I grapple with that?
All models are wrong, some are useful. That's kind of my, simplistic, but I think, so on the one hand, in Geography 5900, where I want to portray and instill some basic information with the students, I may not go fully down this road, because it turns out that, I'm not sure if fact is stranger than fiction, but it is complicated and difficult to find an answer. So in that way, we want to be skeptical, and the thing I like about going this direction is that rather than making subjective or objective decisions and then saying this is the result, what we're trying to do is to look at many possible correct ways of doing it and say, is there agreement, coherence in the answer or not? And in this case, there isn't yet, which now we need to say, well, why is that the case? we haven't studied. I haven't been involved in this long enough to actually circle back on that part.
Every time you say wet or dry, you're actually saying wetter than usual and drier than usual, right? And should convection care about this, or is it the actual value of soil moisture? So maybe, so have you dealt with this in some way?
Right, so good point. Wet or dry in the context of this talk is with respect to normal or expected values at that location for that time of year. So it is not using absolute volumetric water content, in part because the satellites have difficulty accurately giving that, and the percentiles turn out to be a way to standardize and reduce some of the errors. In the Chris Taylor paper, they looked at their wet or dry were with respect to the surrounding area. And so it was a locally derived value to say, if you had a heterogeneous land surface with wet and dry conditions, does the rain fall preferentially over the places that are drier or the places that are wetter? So there's different ways to look at that, and that's another sort of axis that we could bring in this case to say, does the atmosphere care? Because it is a relative thing. So what we really want to get to, what we still hope to get to with the NASA project, even though the radar is inoperable, is this idea of gradients. Because I think that's where we may actually say that we're looking at these, where there's sharp boundaries, these discontinuities in land surface properties. Does that lead to local convergence, or that could trigger additional convection?
Like the forested areas in the Amazon, that sort of thing.
Right.
Yeah.
And so with in-situ data, we don't have a high enough resolution of those gradients. With satellites, maybe we do if we have 1 kilometer. Yep.
I have a question that's more about thinking about environmental data, and in particular under our current political regime. So you have NSF, you have NASA up there, and I know that the president has talked about not caring about monitoring the Earth, only wants data about space, and so I wonder how that, obviously you don't like that. So how does that play into discussions about, about what's possible or what might not be possible, or what's going to be changing in terms of funding or availability of particular data?
Yeah, it's a little bit scary. There is, as you're probably aware, the administration's been a little slow to make some appointments, and so that has maybe been good in that sort of just inertia. Things continue on with the people that were there. There is a new NASA person now in place. And they, depends who you ask, how much influence that will have on the trajectory. There's definitely the public-facing faces, Mars and other planets and those kind of things. Earth science is the easy punching bag. So there is a question. I mean, a lot of these things require not just a year, but decades. And as a climatologist, I kind of joke about being a desktop climatologist because I like to use really long time series, and I can't go out to necessarily a glacier and measure that. So I want to have a record of satellite data or in-situ data or whatever that is decades or centuries, so I can make sure that I'm capturing this. And a concern is not just with radiosondes, not just with in-situ soil moisture, but satellites. If we look at how accurate, I know this is not, in the popular media, there's like, wow, Irma sure was a surprise. And it's like, well, no. Or look at the amount of rainfall from Harvey. Wasn't that surprising? It's like, actually, if you look at the National Hurricane Center forecasts of rainfall or track or whatever, they were really good, really far in advance. And that is because of observing technology and models. And if you take any one of those away, the stool falls over. And so you need really good models, you need really good observations and good scientists. And if there's not funding, all three of those fall down.
Question? when I hear you talk about point observations and then pixels, and you have what statisticians I think call a change of support. You have different levels of observation. Would there be any use in trying to Krieg or model or convert the point layer into something that would be more extensive, in other words, certain models, would that be helpful?
Yes, so we are, through one of the USDA funded projects, taking in situ data with soil characteristics, precipitation, elevation and other parameters, and trying to come up with a 4-kilometer gridded soil moisture product over the United States to help solve some of the challenges associated with the scale. And so it's not as good as having sensors everywhere, but it's an informed guess.
Those typically, those models come with kind of uncertainty measures as well. So it's going to match the point observation and give you kind of a feel around it there. And that could be helpful if you had, I think you're suggesting that taking like a spoonful at one location is not going to tell you a lot about the surrounding area. That might be helpful.
Yeah.
Do you think? Other questions?
So just in the public sector, are the primary consumers of soil moisture and drought data, like, do they feel well served by the current models, and are they kind of invested in any way in the work that you're doing here, like to draw these distinctions?
Yeah, good question. So I didn't really know. I mean, there's some obvious ones when you think about like, well, who uses soil moisture? So there's, in the agricultural sector, certainly utility and interest in soil moisture, and especially at a really high resolution for precision agriculture and applications of irrigation and various things. But in developing the North American Soil Moisture Database, I found all these other users. So it turns out that Enbridge was really interested in the soil moisture data because for construction projects, they want to know when should they start and is their heavy equipment going to get stuck. And so there's a lot of interest in kind of disparate sectors. I promised I was not going to promise myself I was not going to mention power outages today, but whatever, it's going to sneak in. So the connection between this work, which is really where I started, what I'm most interested in some ways, and the power outage stuff is soil moisture. And so what we're pitching to utilities is that, great, you have detailed information on your electrical infrastructure, but you also need a lot of weather and environmental data and soil moisture data to understand the probability of trees being uprooted, the stability of poles, and that this changes in space and time, and that where the SMAP mission, how I first got involved, is as an early adopter where we said we're going to use SMAP soil moisture to force our power outage models as an input to our power outage models. And NASA really likes that because they can then show some economic benefit and do kind of like cost benefit analysis and try and turn it into a dollar amount so that they can justify to Congress and others that here's the return on investment for this sector. So there's a lot of others, but I won't bore you with all. But there are kind of the satellites on their own are probably not good enough. The in situ on its own is probably not good enough, and the models on their own. And so that's one of my interests is in blending, using data from these three sources. And there's some methods out there in the soil moisture literature. They talk about triple co-location, but there's other kinds of ways that we can assimilate observations. So data assimilation class, maybe some of my students will take that on as a challenge to assimilate those observations.
Perhaps time for one more question. Thank you for a very interesting presentation. I wanted to ask about land use. The areas that you show as hotspots are also very intensively agricultural areas, the Great Plains in the West, Sahel, and we know that there's a tight relationship between soil moisture and soil management practices. So I'm wondering to what degree you integrate those into your modeling, but also as part of that recognizing the dynamism and the conflicts over how land is used, not including not to forget the pursuit of agroecological practices, cover cropping, right, leaving residues on soils so that we have better soil conservation. And I think on the note that was brought up about Trumpismo and national science, it's worth mentioning that the question of soils and climate change has now been gagged publicly within USDA and NRCS policy. So as we're talking about this, farmers are being actively discouraged from recognizing the linkages that you're talking about. So I just appreciate that you're discussing this work and restate the question. Yeah, to what extent are you integrating land use into your modeling and recognizing it as a dynamic process?
Yeah, great points. There is a extremely close coupling between land use and land-atmosphere interaction. So we can think about it through what kind of crops are grown in those locations, right, how are they managed, and especially in a lot of these regions, irrigation. So they are transitional or dryland or marginal agricultural for some kinds of crops. And so if we look at the Great Plains of the US, and in Texas, cotton is grown. The only reason cotton's grown there is because there's a huge aquifer underneath that they've been pumping water up for a really long time. That modification of the land surface, that addition of water that certainly serves the crops, but then some of it runs off, some of it infiltrates into the soil, changes the hydrology and climatology, has an influence on the regional climate. And so there's been work that's been done to say how much does all of this additional irrigation add in terms of precipitation and feedbacks, and thinking about these decisions that we're making that have these effects both locally that we can measure. There's been some interest in looking at intensification of severe weather and tornadic activity in the Midwest because of corn and irrigated corn and the changes to the stability of the boundary layer.
Right.
Pretty interesting connection there. So yeah, it's important. It's not, in this work, it's not, we assume, we just take the measurements that we get in terms of the in situ data is in unirrigated sites. The satellite data would integrate all of the sources.
I have one question on modeling kind of related to that. So if you're going to put like a land cover land use classification as an input in your model, are you also like taking like another person's product of predicted like land change in the future?
Yeah, so in this case, we did look at the relationship between land cover and these locations in Oklahoma, but we haven't incorporated land use explicitly in our, for example, bin these events by different land covers, or even to go a step further, which is perhaps what you're suggesting, is that land cover evolves over time, and so we would want to model how land cover may change, and to really understand if we go back just one or two. So this map here is what is the land cover going to be in some of these areas in 2029, and if there are large changes in land cover, that's going to influence latent and sensible heat fluxes, soil moisture, all of these things. So having dynamic land use land cover models is part, if the land surface is important, and I argue that it is, certainly not as important as the ocean, but important. And so then we need to capture those things, human modifications of the land surface, irrigation, conservation, agricultural practices, because it's the sum of all of those that will then produce what happens with precipitation and soil moisture.
Well, on that comprehensive summary, let's thank Dr. Quiring. Thanks to Steve for an excellent talk, and please stay tuned for the future events in our climate series. Thank you so much.